Good evening, I am Mr. Ish. Thank you for joining me for this very quick video over here. If you think about the derivatives and then you think about the variety of integrals, there are more derivation procedures frequently taught for the derivatives and hardly anything presents itself with regards to the integrals. So we can just present something nice, quick and easy. Sine hx hyperbolic sine and cosine hx hyperbolic cosine, they're integrals via algebra. It's not hard by any means, and algebra means you're just doing a manipulation of the algebraic definitions of these in terms of the integral derivations. We know very easily and quickly that hyperbolic sine in terms of its antiderivative is equal to hyperbolic cosine, and you know there'll be a plus c over here for an indefinite integral. You know very well you can do the derivative of this and go back over here. It's like a reverse procedure, and then very likely and easily hyperbolic cosine dx gives you the hyperbolic sine in terms of its antiderivative, and you can reverse this procedure with that derivative. We've looked at the derivations of the sine h and the cosine hx, their derivatives, but let's look very quickly at this integral derivation for sine hx. Remember, this is easy, this is quick, and this is meant to be just an algebraic derivation, nothing more than that. If you write sine hx in terms of this, e to the x minus e to the minus x over 2 dx, this right here is a definition of the hyperbolic sine, and you're taking this in terms of its integral procedure. You will separate everything here across this minus sign. You'll get e to the x over 2 dx, and then you'll have this minus, and then you'll create another e to the minus x over 2 dx. In each case, bring out the 1 over 2, and you can do that. It's not a bad idea to do that. Minus 1 over 2 e to the minus x dx. Now all you have to do is think about the exponential integral template, and I'll put that right over here. Anything which is in appearance of e to the ax dx in terms of its antiderivative is always e to the ax over a plus c. You know that. And that right there is exactly what you have to employ over here. Utilizing exactly this framework, this right here will stay as 1 over 2 e to the x in terms of its antiderivative. And then this right here, you'll have 1 over 2 e to the minus x divided by minus 1, utilizing exactly what you see over here. All you gotta do is this algebra part. You'll have 1 over 2 e to the x. Here you get a plus 1 over 2 e to the minus x plus c. If you combine this into a single fraction form, you'll have e to the x plus e to the minus x plus c. This right here is a definition of hyperbolic cosine, and you know this right here is equal to your hyperbolic cosine plus c, and this derivation procedure for the hyperbolic sine antiderivative or its integral is completed. The hyperbolic cosine goes through a very similar procedure. You're looking at its antiderivative determination or its integral set up in exactly the same way using its definition. Split everything here across the positive sign and bring the 1 over 2 out, and you'll have exactly this for the first part. Then you'll have this 1 over 2, and then you have e to the minus x dx. You will utilize this template here again. The antiderivative of that is easy. It's 1 over 2 e to the x. For this one, you'll have plus 1 over 2 e to the minus x divided by minus 1. This minus 1 will come and affect that positive sign. You'll have 1 over 2 e to the x minus 1 over 2 e to the minus x plus c. You can bring all of this under a single unifying denominator, 2, right? E to the x minus e to the minus x plus c. And this right here is nothing more than you going to the definition of the hyperbolic sine plus c. And this derivation procedure is completed in terms of what is the antiderivative of the hyperbolic cosine, or what is the integral of hyperbolic cosine, and that right there is the hyperbolic sine. The hyperbolic cosine and then the hyperbolic sine are most important of the hyperbolic functions in terms of their derivatives and in terms of their integral procedures, because they're just very common. The only exception to that would be the hyperbolic tangent would be from the other remaining 4 more common. Anyhow, that's it for this video. I hope you enjoyed this video. Thank you for watching. Stay tuned. Have a nice day.